Hello, this first video is a recap of antiderivative rules that would have been learned in Calc 1 that we will be using throughout Calc 2. So the first antiderivative rule is if I have a function that's made up of two or more functions being added together, we can take the antiderivative of that function by taking the antiderivative of each part of the sum. So the antiderivative of a sum is the sum of the antiderivatives. Next rule is that if I have a function that's multiplied by a constant, so C is just a constant, it's just a number, then to take the antiderivative of that constant times the function, we can multiply the constant by the antiderivative of the function. The next rule is that if I want to take the antiderivative of just a constant, so the function we're looking at is the constant function, then the antiderivative is going to be that constant times x plus c. When we're actually writing the antiderivative, we need a plus c because we know that the derivative of any constant is 0. So when we go backwards of taking the derivative of these lines, we should get back to the left-hand column. And so it doesn't matter if I have 5x plus 7, the derivative is 5. If I have 5x plus 12, the derivative is 5. This plus c is representing that constant being added on that just goes away when we take the derivative. So when we take the antiderivative going backwards, we need plus c as that holder for any constant could go here. And so continuing with that idea of antiderivatives are just the opposite of derivatives. We have a power rule for derivatives. We also have a power rule for antiderivatives. That is x to the n plus 1 divided by the new exponent and plus c. So add 1 to the exponent, then divide. We know the derivative of e to the x is e to the x. And so if I wanted to go backwards on that, the antiderivative of e to the x is e to the x. Now, getting into the trig antiderivatives, we know that the derivative of sine is cosine. So going backwards, the antiderivative of cosine is sine. The derivative of cosine is negative sine. You get a negative. So when we take the antiderivative of sine, we get negative cosine. Again, for these antiderivative rules, it will be the case that we can take the derivative of this right-hand column and get back the original function in the left-hand column. Now we have the antiderivatives of secant squared, secant tangent, cosecant, cotangent, and cosecant squared. These all come from known derivatives of trig functions. So we know the derivative of tangent is secant squared. We know the derivative of secant is secant tangent. We know the derivative of cosecant is negative cosecant cotangent. And we know the derivative of cotangent is negative cosecant squared. So we get those negatives for the antiderivatives in the respective cases. But we have all the functions that give us antiderivatives of our trig functions. When it comes to the power rule, there is one case that the power rule can't take care of, and that is when n is equal to -1. Because if I took n equals -1 and added 1, I'd get n equals 0. N plus 1 equals 0. We'd be dividing by 0. We can't do that with the power rule. So we have a different rule to take care of the case of 1 over x, and that is that we know the antiderivative of 1 over x is the natural log of x. Absolute value, because there are many cases when we may be needing a negative. And if we take the derivative of the natural log of -x, we still get 1 over x. And when we take the derivative of the natural log of x, we still get 1 over x. So to account for both of those, we have absolute values. So the absolute values need to be there. And then the last two is we know some given inverse trigs. The derivative of arc sine or sine inverse is 1 over square root 1 minus x squared. And the derivative of arc tangent is 1 over 1 plus x squared. So that then tells us our antiderivative of 1 over the square root 1 minus x squared is sine inverse x plus c, and the antiderivative of 1 over 1 plus x squared is tangent inverse x plus c. So there are majority of our known antiderivatives that we will be using as we continue into Calc 2.